Swayam Prabha. Digital India. Educated India.
All right. To summarize the SVD based LSI model, as we mentioned earlier, it's about reducing the dimension, right? So what we're doing here is to find a new set of dimensions or attribute that capture the variability of the data. So it doesn't matter how big is your term document corpus, right? You can always reduce it in terms of the dimensions. For example, if you have a document size of about 2000 plus and then you have around 20,000 words as vocabulary, unique words. You can represent that in terms of a matrix. That's where you construct your TF IDF as we discussed earlier. So once we have done this, and then in the transform domain what we are having is there is a left singular matrix, a right singular matrix and a singular value matrix, and we spoke about that earlier, right? And then when you reduce the singular matrix size, that's some k from 2000 to 200, we still would be able to reconstruct the original matrix with some small error, right? So that's what we had shown earlier, especially with respect to the image. Even though we had a high resolution image, after the transformation we truncated the SVD to a smaller number, and then we showed that by just slightly increasing that SVD count from 10 to 20 instead of 700 and odd numbers, we were able to reconstruct that image very clearly with about 50 eigenvalues, right? So that's the power of this. Instead of having a very large dimension in the domain that we are looking at the image, we would be able to translate that into the SVD dimensions or the SVD domain, where the value could be reduced, and then we would be able to reconstruct the original image with a very small number of eigenvalues. So that we demonstrated with respect to the image. So if you look at the image, it is possible for you to reconstruct the image with a few patterns. Especially if you look at a gray level image or a black and white image, there could be a certain kernel that we can always find, or the pattern that you can always find, and you can just mix and match those patterns to form an image. So will that work in the case of a natural language or text? How do you deal with that? There are patterns within the text that we have. We should be able to reduce the dimension, but how do you deal with those small ones, where the frequency of the word is only 1 or 2? So out of 20,000 words that you will find as vocabulary or the unique words or tokens, only about 100 or 200 of them would be having a very high frequency. The rest of them would be having very small numbers, especially the vocabulary with the count of 1, or the words with the count of 1 would be having a large set. Will that contribute anything to the in our case, especially in the query modeling, in terms of retrieving the document based on keywords, or trying to classify the document based on the set of keywords? Don't we consider them as noise? And will they really have some impact in the dimension that we are talking about? Let's see how we can do with by taking some small examples. Okay, as I'm going to be taking about 2 examples to showcase that. So we want to identify the strong pattern in the data. So that's the idea, right? So if you look at the eigenvalues, we know that it is in the descending order with respect to the magnitude, correct? So this contributes the maximum, and then we know that this contributes to the lowest. That is why we are able to cut and then reduce the dimension, and we are still we are still reconstructing the original document with minimal error, right. So we also know that the most variability is captured by the small set of values. Okay. Patterns among the terms are captured by the left singular values. We have the left singular value here, right, U, and then we have the right singular matrix V, right. So the patterns related to the documents are captured by this. So if you have terms and document organization, where each one or the each cell in this matrix represent the word in that particular document, correct. And then the left singular one captures the term related features. So the eigenvectors associated with the largest eigenvalues indicate the direction of the largest variance. So this captures the largest variance. If you take these matrices, right, and then find the eigenvectors associated with this one, okay, you will find, or the vectors would indicate the direction of largest variance. So again, if you take the second one, which is orthogonal to the previous one that we computed, but will give you the rest of the direction, not rest of the some direction, and third one will give you the next level, fourth one the next level, and so on and so forth, and then the last one will be the least one and probably would give you very little or very small number of directions. Okay. So we have seen this through the image demo. So now let us look at it through a text. Okay, I am going to be showing two demos. So I am opening it in the Colab. So what I have in this demo is I have a set of documents. These documents are coming from the kinematics problem statements. Okay, so I have about 271 documents related to the problems in kinematics, and that is what I am using it as my corpus. So this you may also use it. This is available publicly. You can use this. Okay. So here this is the location of the corpus. I think there is a duplicate here. We can remove this. And then I am reading that corpus from the location using a pandas function called read CSV. So this reads the file, and each document is separated by a new line, and there is no header related to that. And then I have a small pre-processing function which takes away all the numeric values, and then it tokenizes after that. Okay. I am just creating a text initially which contains all the tokens related to 271 documents, and then I create a dictionary with respect to the vocabulary of the words used there. Okay. And then if you go and then look at the document dictionary, right, that is very important for you to do that. That is an important step. You have to find out how many words are there in the vocabulary. Okay, so you need to get the count of that. So in this case it is about 900 plus. Okay, and I have restricted the count to 700. See here I am not using any stop words or any other mechanism in the pre-processing. I am just removing the numeric and then tokenizing that. Okay. So, out of 900 I am just saying okay, let us keep only about 700. So, now your document size is 271, the number of words is 700. Okay. And then convert the dictionary into the bag of words. Okay. So, for every document or every token in the text that we have created here, so we are creating a bag of words, right. So, that contains your document term matrix as well. And then using that text that we have already created by the pre-processing, we also need to find out the term TF-IDF, right. So, that is our aim. So, the entire matrix now contains the TF-IDF values. So, your column contains the documents, the rows are the words, and every cell that you have in that matrix is a TF-IDF. It contains the TF-IDF value. Okay. So, once you create the TF-IDF, now we can use an LSI. So, here I am using GenSim as the library. So, I do not have to write a lot of code in terms of creating the SVD and so on. Maybe additionally you may want to write 5 or 6 lines if you use NumPy. So, in this case I relied on the GenSim library to do the job for me. So, there are several other libraries available, you can try each one of them as well. Okay, so, what I have done is I have just created a TF-IDF and a model, and then I am using the LSI which will now create our U, sigma and V, right. So, here to show that the number of topics here refers to the sigma values or the k values that we are talking about in the eigen matrix. Okay. So, I have just kept it as 1, I have just taken only the top one here. So, you remember even the image processing we started with the lowest one and then reconstructed the image, and then see added one more, and then slowly as we add more and more, the image started becoming clearer and clearer, from a blurry picture to clearer picture within about 80 or 90 eigen values. So, in this case again I am doing the same thing, I am starting with 1 and let us see what happens. So, in this case what I am also doing is, instead of classifying the document, I am going to use the query function. I am going to have 3 or 4 query parameters. In this case I have 4, and then query the transform domain and finally get the values in the domain that we are dealing with, okay, to find out what documents are retrieved based on the query. So, for you to do that, the query has to be converted into the SVD domain, right, or the LSI domain. So, we first create that LSI model using the sigma as 1, and then using the dictionary which contains the word ID to the word, and then using the TF-IDF. Okay. And then the query document contains car acceleration velocity for. So, now I have to create a query in the LSI domain as well. So, again I create a dictionary of that and then create a vector for the query in the LSI domain, okay. That is available in this. And then there is a similarity function that is also available as part of the GenSim library, and then it goes and then looks at all the documents related to the query and then provides you a score for each one of those. Okay. Remember the cosine distance that we computed earlier in a very similar fashion. This extracts all the similar values and then keeps it, and you can only list 5 of them, 10 of them, 20 of them in any order that you want to list them. Okay, so it first gets you the similarities for the queries, and then you sort it, okay, and then finally print this. So, in this case I have used my k as 1. So, you see that it says all documents are equal. So, it has not found anything. It is not very similar to what we saw in the image, is not it? So, there we saw at least some portions of the image being reconstructed, we could recognize, whereas in this case you can see all kinds of jumble, even though you see a car is in the second one, but the similarity values are all equal. That is not the right thing. So, let us now try to increase it by another, and let us see what happens. So, we can see that the similarity value changes and we start seeing the query related document, right. So, car acceleration velocity far. So, we have a race car, the first one contains all the values related to that, second one, third, the speed of the car. So, there is a dragster also. So, what has happened here? So, it is able to find a document which does not have the word car. You remember the idea of having the distributed embedding is to find the similar terms. So, it is somehow able to find the dragster is similar to the car, okay. And then we can see many car related documents here. Even you can see a jalopy there, and then there is a bike I saw somewhere, okay. So, the document that contains similar values as in the query are now listed. I have just increased the sigma value by 2. So, by just increasing this to let us say 5. So, it is now even more sharpening the results there better than what we saw earlier. So, you can now see that, right. So, lots of car in front in the queries. Okay. So, if you go down here, you will see the similarity value getting reduced, and then towards the end just because it managed to find a few keywords, it gave very smaller values for those documents, right. So, you can increase it to 10 or 15, let us say we will increase it to 15 and see what happens. It is changing it slightly, but we can see all the documents related to that are found. Okay. So, you also want to go through this and then look at the data, change the query parameters and then see whether you are getting this value or not. Okay. So, you can look at the corpus closely, change the query parameters and then change these parameters as well, and then find out how this particular application behaves. Okay. So, this is one example that I have shown where we have a TF-IDF based term document matrix. We used LSI, and then in the reduced domain we try to find the similarities between the query and the document, between the query and every document in the corpus.